Good. So this is a panel discussion, how we learn to stop worrying and love the cloud. There is a movie reference in there, being from LA. I'll let you work that out if you want. And John is our moderator. John, take it away.
Okay. It's the first time anyone's accused me of being moderate. Backward. So that's Peter Sellers for people who get the movie reference. So, 2-3 years ago, if you'd come to VidTrans and you talked about the cloud, there was this consensus of, oh, that could be neat, right? Maybe like 5 years ago, people were like, oh, that could be neat. We might use that one day. But with that sort of voice of, yeah, and we might do 3D, and we might do all kinds of other stuff. And somehow, over the past couple of years, we've built enough experience base as an industry to go from thinking about it, to trying it, to playing with it a little, to now we're at this point as an industry where we kind of have learned to stop worrying and to say, okay, you notice the subtle shift in the papers you've heard so far today to less about can it and more of how would you, how do you, how do you make this usable? And so I'd like to introduce my fellow panelists here. So Andy Rayner from Nevion, a Sony company. Did I say that correctly?
You did. Perfect.
And Kieran Kunhya from OBS.TV.
Open Broadcast Systems, not to be confused with the streaming software.
Okay. That's not the Olympics OBS. It's
all that one too. Yeah.
They're all very good.
Yes, lots of OBSs in our world.
While you're on that slide, John, can I ask you a question? What do we mean by cloud?
Well,
How long have you got?
For
the purposes of this presentation.
Well, no, this is an important concept because if you ask somebody on your executive team, should we do stuff in the cloud? They'd say, of course. But then if you ask them what they mean by cloud, they would say, well, that fluffy thing, or something. Every person who uses the term cloud has a different set of meanings and implications that they have in their head when they use that word. So what we've tried to do in the deliberations of some of the working groups is to literally not use the word cloud. Because doing that forces you to say what you really meant. Did you really mean a multi-tenant public hosted environment? Okay, then say that. Did you really mean a pile of computers in your own data center? Okay, say that. Because all those things in different parlances might be construed as cloud. And the work we're doing is really about how do we deploy and manage and use software-based systems in a flexible computing environment, to be a little more generic. So that said, we've kind of, as an industry, come over this hurdle from could it work, what are all the risks, what are all the problems, to, okay, we understand the bounding box, we understand the set of problems. Sir?
I have a definition.
I'm sure you do. Okay.
We've got the mic on the floor.
All right.
Do you need to turn it on, pull it towards you, the switch?
I will briefly yield the floor to Mr. Edwards from a well-known cloud service provider.
It should be on.
Parliamentary procedure. Right, honourable gentleman.
Should be working.
Okay. 2.
We lost the launch.
Cloud computing is the on-demand delivery of compute power, database storage, applications, and other IT resources through cloud services platform via the internet with pay-as-you-go pricing. Thank you.
Wow.
Okay.
That's quite a narrow definition compared with what we're using then.
Exactly.
And now for the representative from Google. Okay, but in our case, because many customers are interested in hybrid and in on-prem plus cloud and in scale to cloud, we've been trying to keep the work we're doing a little more genericized than that, because both models, people want to investigate these things. So all that said, where were we when we were so rudely interrupted?
We were about to change slides.
Yes.
And jump into the
How
next
we got
topic.
here. So, to get adoption, this, like Chris Lennon talked about this morning, right? What are the impediments to really using this stuff for real? One of the impediments, wow, I wish there was a way that was bigger.
Can you make this full screen? Because we've got like
Well,
notes.
no, that's the preview, unfortunately.
The preview.
But the preview, you can scale the preview so we actually see the slide. All we can see at the moment is
The
me
notes
know.
the
section.
notes
is-
which
yeah,
don't
there we
exist.
go.
Ah,
Awesome.
thank you.
Because I can't, this was tiny. What are the barriers to adoption? So you're all familiar with, who's the guy, Christensen? The source of that picture on the bottom. It's from a well-known book called
right.
Crossing the Chasm is the name of the book.
Okay.
And, yeah, that graph right there. So, it really is the question of, early adopters will put up, or innovators, and the first part of those early adopters, they'll put up with a lot of rough edges. To get to the real market, which is our focus, right, is what are the standards, what are the things that have to be in place for the real market of using the cloud to do television work? Here I go, using the flexible computing environment to do television work. What do you got to have? So, multi-vendor interoperability with standard APIs. Sounds great. How do we get there?
Small s on that standard and
Well, yes.
small s on that. Do you mind questions? Or
Oh, no, interactive questions are the best kind, to a point.
So capital S standards would imply like ISO, IEC, blah, 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 standard. Or standard, small s implies vendor, publicly published, blah, blah.
I would say small s is, happens quickly enough to be relevant. But, equally, you got to have appropriate to task picture quality, which again doesn't mean perfect for everything, but appropriate to task for each task. You got to have some well-defined way to get signals from the ground to the cloud and from the cloud back, and you got to have mechanisms for building workflows. All these things are important and good, and that's what we're working toward. So that's been the goal. Either you want to add anything to that, or let's...
No, I think that's very well summed up.
fair.
Yeah.
Right. So now it's about how would we get there? Because there's a lot of organizations that are sort of involved. A lot of these things cross over into the IT space, and we'd be well advised to use things from the IT space to the extent that they're relevant. So what are the challenges? Well, Kieran, what are the challenges? Why is this hard? It's your slide.
Yeah, it's my slide. So key challenges, we need to integrate with the ground both ways, and these existing workflows are well-defined linear timing workflows. Thank you. So SDI, ST2110, satellite cable, over the air. So this is quite a bit different from a lot of the quote-unquote cloud production you see in press releases where it's going straight to web, where that's a non-linear sort of workflow. And these two sort of legacy, well, 2110 is not really legacy, but they have well-defined linear timing models. SDI, 2110-21, VBVs. And so without such a proper timing model, you have either variable or undefined latency. This is one of the reasons your web streams are 20 to 30 seconds behind broadcasts. These guys don't have timing models. They just pick a delay that's large enough and hope for the best. So why are my neighbors cheering? And it's also important to think about when you need to cut between the ground and the cloud, or even between sources in the cloud. This requires a timing model, because you don't want to sort of see a goal happen again from a different angle, or see a car overtake another car. This all needs to be timed correctly. And it's quite a bit different from where a lot of the sort of promotion is, which is in the consumer space, where since it's the final step in the chain, they don't really care about this timing as much as people doing production.
And I think it's fair to say that throwing buffering at things is a good way to get things to work. And, and John and I have been talking about this a long time, even in a 2110 environment, we throw unnecessary buffering in the way most vendors are implementing, even on the ground 2110 in environments, just because that's the easy way of getting things to work. And I'll be talking to that a little bit more tomorrow morning as part of.
Yeah, I think this intercutting point is especially problematic, right? If you think about cloud-based elements and ground-based elements in a production that has both, there's this real interesting problem of, okay, I launched the game feed up to the cloud, and I'm doing some stuff on the ground, and the cloud maybe it's making a VR or some other neat thing. When I pull that back in, how late is it? Is there a bound on that lateness? Or
Is
am I
there a
gonna
consistency
be,
on that
is it
lateness?
consistent? And, because otherwise you're faced with, on the fly during the show, you're trying to like bang that delay back in, and nobody wants to be in that zone, right? You got to have a timing model that's consistent, but you also don't want to overdo it. And that's something we're super worried about as a group, is figuring out how do we get a timing model that's good without going crazy. So then there's getting things between instances. So this is something, again, we talked about this morning orchestration, how do you stand up parts, and we talked about like the Catena work on control and how do you talk to the pieces from a control plane standpoint. But the media plane, the data plane between things in the cloud, if you buy some applications from different vendors and you want to string them together in a data plane, how's that work?
And
Andy, how's that work?
so just to clarify the use of words, because I think you used the word between instances, and in certain providers that means a specific thing. I think what we're talking about is the provision of getting data, media data flows between the next media function that we've instantiated.
You mean the next microservice element?
Yes, whichever
Okay.
you want to use. Yes, but so we're not talking about going into instance in specific public cloud service provision. But the two key things we want, and we have got very used to in the 2110 world, we lovingly spent a lot of time on the -21 proposal, which was how we time data. And the reason we went very, very, very carefully on defining timing was because we don't want to lose data. Because unless things are actually spread out properly in a UDP world, when we interconnect, there's a risk of losing stuff if we don't have things spread out and managed. So we actually had a way of doing that. And in the cloud, we have a same requirement, but potentially we're not going to be using vanilla UDP. We actually want other technologies but we do need the same end goal, which is deterministic connectivity, as in we want it lossless, and it needs to be transacted within a time-bound period.
But a key point of all this, if you think about the traditional capital S standards world, SDI, for example, it's defined all the way up from the BNC connector. So there's a set of standards that, by reference, go all the way from the concept of colorimetry down to the shape of the connector. And that's good, because you can build stuff and plug in cables and all that. But it's also bad, because it doesn't create proper layers of the model, except as we've gone back and helped it through the standards process. Now, in the public and hosted environments and in the private data center environments, there may be different optimizations of how to get stuff between elements within a microservices array. Right? In some places, it may be that you've got fancy network adapters that do some specific thing. In other places, maybe you just open a socket and slam some bits through. Well, we wanted to figure out, how do you draw a line? What is the line of demarcation between what we should, small s, standardize or commonize, if you will, and what should we leave to be part of the environment? And so we kind of said, okay, we're going to depend on the cloud provider if you're in a cloud, and on some layer within say a private data center if you're in one of those, to get data moved from thing to thing, rather than trying to detail it all the way down to the IP packet or all the way down to the electron. And so that's important. And we said the only thing it really has to do is to have a bounded latency. It has to be that when I say I'm done, next guy, that it gets there in some bounded amount of time. And that seems to be a demarcation that people have been okay with in all the different instances we've looked at.
So we make those assumptions, basically.
Yeah, that's an assumption in
There's
our
an
working
assumption
group.
that happens below there. It's integral and time-bound.
So by the way, there is a working group. So in case we seem like we've never met each other before, there is a working group. We I'll say we work. We at least meet every Thursday. And it's really about addressing this set of problems. And it's about, what are the last set of difficult problems for, compute-based production.
For it to be interoperable and to work across the industry, because some people are creating their own environments that actually probably work quite effectively, but that's not an industry compatible approach.
So there was a slight, well, there's two broad approaches people are taking at the moment, which is one,
A bit closer to him. That's the...
I don't think Kieran's mic is on. Oh, it is now.
It is on. That's better. That's much better. Okay. Yes. So there's two sorts of approaches people are taking. One is a monolithic, usually single vendor system that's doing all sorts of different things, and obviously you lose the benefits of value that individual vendors have. You're stuck with that single vendor, or they're doing proprietary transport. I think the most obvious being NDI, as we saw in the previous presentation. And so the GCCG working group would allow for an open set of transport that may be cloud vendor specific, may not be, and a non-monolithic, building pipelines, building workflow steps, as we do on the ground, but with a defined timing model, and we'll talk about allowing more flexibility with timing than we do on the ground.
So customers can have a best of breed selection of the different functions in the broadcast production environment as they do currently enjoy.
So all that said, so there's a working group. So the first thing we tried to challenge ourselves on is, okay, how do you get there and how do you get home? And then we'll worry about how you get from place to place inside. But equally, these are in a funny order now. We hit a few slides, and I think we hit the one I was expecting there.
Maybe the next one.
Yeah,
Skip forward.
We'll come back. So,
Yeah, there we go. That's what you want.
So we looked at how are people getting to the cloud today? How are people getting home today? And we kind of enumerated all the different things people thought they knew people were using. Everything from uncompressed all the way down to, Zoom, GoToMeeting kind of quality of video. And all these are used in practice to get stuff into cloud-based production. And you got to pick the one. But we said, well, let's pick a few operating points that are pretty common. So we said, well, first there's a sort of interactive latency, 20-ish megabits restricted VBV kind of H.264 coding. And this is pretty common. People use this for interviews and remotes and stuff where you want to have a pretty low latency. I'm sure the risk team could tell you all kinds of things about that. And then we said, well, there's also a next level up of that that's H.264, still constrained VBV, but running at higher rates and really more strongly constrained to get really good low latency. As opposed to the lower one is more bandwidth optimized, maybe the latency is a little longer so you can get into that low rate. But the middle one there is really optimized, spend more bits to get a very short latency because people can't tolerate the latency. And then, of course, there's if what you really care about is super picture quality and all these things, then you would use kind of like JPEG XS with, again, some optimized transport. And there were a couple different transports in play that people talked about. In the end, we published this TR09 that describes some part of that. Can you talk a little bit about TR09 and what it is and what it does?
Yes, so TR09 has actually been published since the last time we met, so probably a worthwhile plug, although I've got one slide to plug on it tomorrow. Basically, it defines two things. It defines the data plane and the control plane when you're going between locations, so when you're going over any kind of DMZ WAN environment. So it defines the profiles and the way
Mr. Simpson, we've saved you a chair up here, sir.
So it defines the protection, the file format, the formatting of the data, et cetera, in the data plane. And then what took the most time in TR09 was defining the control plane, and that's a way of securely advertising and sharing resources from one location to another between what will probably be different entities, although it could be the same organization. So the control plane and the way you actually transact the requesting and the sharing of those resources. And we use what we call a constrained version of some of the NMOS protocols there.
Right. So who here knows what a PGAD is? More than a few. This Tier 09 describes how you would do a PGAD in an IP environment. Right?
Yeah.
It's an important problem, right? We live with it every day. But, you know, how do you do it? So this provides us that way to make sort of good connections between arm's length parties. And it turns out one of the arm's length parties is the front door of the cloud. So anyway, so we picked these operating points. But, you know, if you think about the overall scheme of things, there's a couple other operating points that matter a lot, right? So when you're sending stuff to or from the cloud, it's kind of defined all the way at the bottom of the stack. You know, down at the IP packets, there's a set of standards you can read that are all the way down to the bits. And the same thing getting home, you know, there's a set of standards you can read that are all the way down to the bits. But in between stuff inside the computing environment, where's the right place to draw this line, to draw the interoperation point? Because you don't necessarily want to define each of these things all the way down to the packets on this internal network, because it's the right solution probably depends on the overall system and what each provider offers and so forth. So that's where we said, well, we're going to pick an interoperation point that's way up here at kind of the buffer level, and then make it the responsibility of the environment you're running in to provide a way to get a buffer of stuff to the next thing in line. So that's...
The yellow bits.
Yeah. So that was kind of a key thing we agreed early on, is that was the right place to draw that interoperation plane, was not down at the packets level, but up at the, you know, handing off data structures kind of level.
So it sits above that supplier-specific abstraction layer that we were talking about earlier.
Can we do an audience Q&A now, if anyone has questions? Because we want this to be educational.
Well, what I'd say is, if anyone's got any questions, just walk up to
Yeah,
that
just walk
mic
up to the mic at
whenever,
any
just
point.
like Thomas led by
Yeah,
example.
We've
earlier
had
on.
other people ask questions. Feel free.
Yeah,
Although we
yeah.
don't have Gilmer here to keep order, so we'll need to appoint a bouncer if y'all get in trouble.
I'll take care of it.
Yeah.
I'll nominate myself for that.
Okay.
Any questions then on what we're
Right.
trying to achieve?
So as the slide says, the signal plane might actually be the easy part. So there's a lot of work that's gone on. There's some work in progress. There's some work underway. So during the last, couple months, or 6 months, 9 months, the VSF, we've published this TR07 and TR08, which are both how you do JPEG XS between things. So one is how you do it the old way with transport stream. The other is how you do it the new way with 2110 wrapping. The JPEG XS is the same either way. The picture quality is the same either way. It's just, like we talked about earlier, anything worth doing as an industry, we come up with 2 different ways to do it. So there we did also. Then TR09 we just talked about. It's about the encapsulation plane, but also the control plane of how do you organize these arm's length transactions. On the middle cases with transport streams, we decided there wasn't anything value we were going to add to documenting that, except that, in RISC, there's a lot of work that's been done on that. And there is some work in the AMWA going on now around defining, belatedly 20 years later than we should have, a common control plane for transport stream endpoints. I don't know how we got to 2023 without doing that, but as an industry, shame on us. But then we started talking about, between things in the cloud, how do we keep track of time? And Wes, you've sat through a lot of these meetings. What's the problem? Why is this hard?
Well, the problem is, first of all, you need to have accurate timing only at very specific points along your production chain. In other words, yeah, when the camera's sampling video, taking pictures every 30th of a second or whatnot, you need very accurate timing. when you are displaying that video to a human, you need to have very accurate timing. But in between, well, you don't really have to keep everything locked in step. And the other problem, of course, is that there is no common timing reference within the cloud environment. You can get pretty close. There are some third-party cloud providers that are talking about, and I believe some of them are already offering, PTP as a service. But does it really make sense? And in my humble opinion, no. You need to make sure that you've got linear, time-accurate capture. You need to make sure that you have linear, time-accurate display. But everything in the middle, if you don't need it, why make your life more difficult? And that opens up a huge range of possibilities for processing. You can distribute, you can have some processes that work on multiple frames at a time. You can distribute those. You can collect the results back. Actually, audio is a lot more difficult than the video side of things. But why force yourself to do something in a lockstep, frame synchronous way in the cloud when you don't have to?
But the important thing that goes alongside that is those accurate timestamps that we used on acquisition of both the video and the audio and any other real-time data that's being generated. The timestamps need to be propagated through the chain. So when we're in this fluid world of doing the compute and processing stuff, we actually are entirely aware of the accurate, what time is related to each of those clumps of media that we're processing.
Right. Now, one of the things I've observed over the years in different groups of people trying to write technical specs is every document is a little bit of a reaction to the mistakes you made in the last one. So, like in 2110, we were super, super strict about, packet spacing and packet clumping and stuff. Why? Because how'd we do it in 2022-6, Andy? It was the Wild West, right?
Absolutely.
There was no spec at all about burstiness or anything, and there were a lot of actual problems caused by it. So in 2110, we overreacted the other direction. So here, are we overreacting in the other direction again?
I don't think we're overreacting. I mean, my biggest regret on 2110 as a standard is that we didn't mandate the propagation of that origination timestamp through the process, because that would have made so many things that we do in the production environment so much simpler. And in fact, the work we're doing in SIMPTE now with -11 called timing planes is an attempt to retrospectively fix what we missed out in the definitions of 2110. So what we made a determined effort in this work that we weren't going to make that mistake. And it's even more important because at least in 2110, we've got a traditional linear push timing model where everything stays in step as we propagate through the system. Whereas in the compute world, compute is inherently non-linear in the way it likes to work. So it's even more important that those actual timestamps of capture are actually propagated and kept associated with that frame of data or with that audio sample as we do all the processes downstream.
Yep. No, we're not fixing, we're improving.
We're improving.
We're enhancing, yes. But now, in addition, one of the things that, again, in a traditional facility on the ground, it's like you try to have everything synced up to the same clock. Well, in the cloud, you don't necessarily have that time source, and even if you did, it may not be the time source of the production on the ground. At the end of the day, there's a truck outside a venue, it's got an oscillator, it can't see the sky, it's not GPS locked. Whatever it sends you is what you got. So you can either lock to it, or you can lock it to you later on the hard way by, skipping frames and stuff. But it'd be good if we could actually propagate ground time through this whole workflow and return to remerge with ground time in a fixed latency of the whole thing without having to worry about all the little parts in between too much. So that's what we've been working on that's a little bit difficult, is that timing model to give us all the flexibility we want and yet not mess up all the things we know are important. So how do we recreate, how do we not recreate the lockstep tight timing pipeline in the cloud? How do we do it right instead?
Kieran, that's.
Kieran,
That's my question.
someone other than me should talk. Go ahead.
Okay, yeah. The cloud is a shared resource. So things may, for some reason, run slightly faster or run slightly slower for various design reasons, be that CPU or something like that. But what we need to know is really the worst case of how long can something take in the worst case, and we can sum all of those up, and the thing at the end that needs to output something linear, usually to send back to the ground, so a transport stream or something linear, can go and figure out how to make a linear output. So everything in between the ingest and the egress can have some level of time variability, just as long as we know the worst case, which is obviously quite different to what we do on the ground currently, where on the ground things are very lockstep. We push frames out at very fixed intervals. And this is very beneficial to software implementations.
Yep. So we had to come up with a model. And being engineers and doing math, we said, well, basically, things you run, they take a certain amount of time, except when they don't.
Sounds like a true engineer.
Yeah. So we said, well, what's the parameter, right? So basically, for everything you do, you wind up speccing what's the fastest it could happen, because it's sort of worth knowing that sometimes, and what's the 99.9% of the time worst case. And it turns out most applications are characterizable that way. And so those turn out to be composable, meaning that if you know the step A time and you know the step B time, you can figure out the output of step B, because it's the sum of the minimum is the sum of the two minimums, and the maximum works out to be the sum of the two maximums. And then there's about 5 pages of definitions in the spec around those words and how they work, because there's a lot of work under that.
It's worth also pointing out that in a compute environment, the value of what we're calling in the document T99 is actually obviously dependent on the specific instantiation that you're doing of that. So unlike a traditional appliance process, which may say, I know that's a one-frame process, and I know I'm guaranteed to get it out 1 frame later, depending on what instance on you or what compute power you're running it and what processor speed, then that T99 value is going to be different. So it's a non-static value.
Right, but it's static for a given instantiation.
Yes.
That's the key. Because you don't necessarily know until you actually, your orchestration system stands up the thing. You don't know, is it going to land on a 2 gigahertz blade? Is it going to land on a 2.2 gigahertz blade? It's sort of, until it's stood up, you may not know. You may think you know. You may know what you asked for. But the reality is that, these specs have to be built into a dynamic workflow. So it's not just defining these things so that you can write in your Ansible script how to do it. It's really creating a system that when it's stood up can predict its own latency and meet it with high reliability. Because at the end of the chain, whether you're compressing the signal to return to the ground, or you're going to turn it into little thumbnails to show to a user or an editor or somebody, you have to know how much buffering to use to optimize the latency. So we've been working on this a while. How do we finish? Wes, how do we finish?
Well, to me, the difficulty is finding common ground between all of the platforms. In other words, we've got to figure out a way to define this data and a way to represent it, and then a way to expose all that data to a control system that can actually do these calculations. And that's a tricky part.
Right, and even the concept of should this timing calculation be done by some external, supervisor function, or should it be, created along the data path? In other words, if you know the timing of your inputs, you can predict the timing of your output. And ultimately, if you're the thing that has to do the linearizing operation, you're the one who cares about how much buffering do I need. So there's a whole school of thought that, I don't know, I'm the chaser of maybe, that things ought to be able to self-assemble. That doesn't mean that necessarily every case will always want to self-assemble, but there ought to be enough data in the control flow that things can self-assemble and know how much buffering they need and not just lob an extra few seconds in case.
And
Well,
that's-
and not only that, you have to have some way of exposing the result of that calculation so that you can determine whether it's going to work or not work for your application. There's got to be a little bit of parental oversight, if you will.
Yeah, one of the things we've got in the spec is sort of a list of what are the things that have to be exposed through an API and what are the things that have to flow, to the next thing in the chain. And it's sort of nice to hear in the discussions today and tomorrow, you'll hear different talks talk about the plug and play elements. You can kind of see all the pieces that go with how do we solve this problem as an industry are each getting worked separately. So I don't know, I was pretty excited so far. We'll see what tomorrow has.
I think Wes has one of the biggest challenges in the education aspect of things, arguably harder than the engineering in some ways. I think things like PTP in 2110 was half a decade, even more of industry explanation, and this is going to be similar, trying to explain T99's summation of latencies, time tags, clocks.
If we do a good enough job of writing the document, people could read it.
Yeah, but they don't do that.
No.
We know that. No, and just to follow along with that, I think the most important thing is the common vernacular, the common glossary, if you will, so that everybody knows what you're talking about when you talk about a T99. That's going to be critical for our industry to be able to communicate within it and to be able to explain to people that are close to our industry or curious about it, what it is that we're doing. Why do we have these things? To me, the job is always, if somebody gives you a control surface and you've got all these different things that you can, all these, I always like to say knobs that you can twiddle. What happens when you twiddle the knob? And that's going to be a little bit of a challenge, I think, in this entire setup.
Okay.
Hello.
Now, what can you do to help? Is the important.
That's what
bullet
Gerald
out
was
here.
going to ask.
Can I ask
Gerald.
awkward questions? Can I have
Yeah,
that?
but
So I've
no,
got two
questions
questions.
are good. We've come to the point where, if you have questions, we may or may not have answers.
So
But we have
my first one
opportunities for you
is
to
first one
help
is T99. So my first question is about T99.
Yeah.
So I'm guessing you don't mean T99. You probably mean T99 point lots of nines.
Yes.
I'm wondering what your lots of nines is and I'm wondering if you have a fallback behavior that you're going to impose when you fail that, because you build your Gaussian curve like you did, but you can't build a Gaussian curve that will give you T100. So when you fail T99 point as many nines as you like, and you don't end up with an answer in the right time zone, so you can't provide the
But we
non-gapped
have
output.
this problem already. What's the phrase? Quasi-error-free.
Yeah. This is very much. You remember years and years ago we used to talk about error correcting codes and FEC on systems and how much FEC do you need. And there's a very similar problem of, yes, chasing Xeno all the way down to 100% is implausible. So that's why we kind of said 99.9. So, one frame out of 1,000 could be late.
But
That's
that's
not
quite
very
a,
satisfying,
that's
is
quite
it?
a few an hour, right? So what I'm asking is, what is the backstop? Are you expecting bits of kit to frame repeat or resynchronize, or what are you expecting?
I think we copped out and said application dependent.
Yeah.
So
I think it really depends on what you're doing.
I think you're right, Gerard. The behaviour of the downstream equipment, if the system fails, is
Well,
something that has to be.
When it fails,
Say again.
When it fails.
When it fails, absolutely.
In your T 0.
But the other question is, what level of margin do we build in?
Yep.
So if we say, our T99 is 4.5 milliseconds, then in the control system, the supervisory system, it may say, okay, I'm going to give that 7 milliseconds. So you could choose boundaries of tolerance, and we haven't. Okay. That's going to be application.
But as long as there is a bound to begin with, it's not like with web at the moment they just pick 5 seconds, because they know that will always work. But actually, that may be way too much, or that may be way too little. So things like NDI, that's sort of an animated GIF just pushing frames at a time. In some ways, quite similar to the linear lockstep model. And actually, we want something in between where we can bound this. The point of an upper bound, by definition, is not the exact number. It is something rough and close enough that will work in the real world.
It feels like it's a close answer, but I still don't think it's worthy of a cigar, in the sense that this 99 point something, it's always going to fail. And
Right.
So you might as well build in the behaviors you expect when it does fail.
Absolutely.
Otherwise,
Yes, but we're not defining in this work the media processing functions themselves.
I'm agreeing, but you're defining a failure already.
We're defining the ecosystem in which they run.
I'll go to my next one.
I don't think it. I disagree, but we can have this discussion afterwards. Because
Go ahead.
no. I mean, we're a software company. We build products. We have upper bounds to the things that we do already. And in theory, you can have. I have a few sequences in our office that manage to create the most mathematically impossible things that you've ever thought would ever exist, but they pick the worst cases of GOP structures and then suddenly flip to a literal mathematical inverse of that, and that happens, but we live with that in the real world, and it's very, very rare. It's once every 2 years you get this clip that happens to do the worst thing, and it's rare, and this is a similar sort of pragmatic problem that you have in the world.
Right. And the point is that we're not going to dictate the behavior of the system. That's very much application dependent. I mean, in some cases you may, if you're recording something for archival purposes or something like that, you may allow, more things to accumulate. We can't define what every system has to do when T99 is exceeded.
Then I think you probably need to make it very clear that T99 is going to fail, and endpoint,
Yeah.
and either senders or receivers in your model have got to somehow either push out an extra one or repeat an extra one. Or do something clever.
Probably the thing at the end doing the distribution encode will either have a little blip and then the whole downstream will blip like it does now. Like I could lose a line of SDI and we'll just blip and probably no one will even notice because the whole signal chain as we've designed it will hide that.
But I think what we have done here is sort of to create where does that failure happen. So rather than forcing every single piece of the puzzle to sort of independently do something about, I missed the VSync, we push the whole problem and the accumulation of things to the point where it actually has to be linearized. So we've added a statistical help there that the only time you'd reach that problem is if every single piece of the chain violated its T99.
So that's my next question then, because most
you've probably bought back all the margin.
Most production workflows are not linear in the sense of A followed by B followed by C. They're kind of trees. They're trees that arrive, inverse trees that arrive at an answer.
Yes.
What you've described as a single terminating timing plane, how are you going to deal with the fact that most productions are built with many, many timing planes that arrive together? So
there's a document. So we actually spent a lot of time talking about this case, and there's a few sub-cases.
We have examples.
If you're at the end trying to linearize back to a linear delivery, you need to know the bounding of the buffering and how much delay to put there. If you're at a waypoint in the middle where you have to reconcile two things, you don't necessarily have to linearize them, but you have to reconcile them to each other. We also have a well-defined model of when is the time you can do that. So it's a similar buffer question, but you aren't actually delaying anything. You're just, you're delaying one to match the other if you have to compose them, for example. So we actually do have math in the document for both those cases, the waypoint where they combine and also the linearization case at the end.
Okay, thank you.
And we also have addressed what tolerance, the concept of needing to introduce tolerance to allow for the fact that something may be switched in that's more latent. So if you've got a dynamic tree, as you describe, where you could actually architect the design such that you can actually accommodate for another media function that may occasionally need to be switched in, or whatever else that needs to come in to actually allow for that time budget in the way that the time budget's mapped.
Yeah, especially things like backup feeds, where you have your primary feed, your backup feed happens to be later, because that just is, that's life. And so you make sure you introduce the right amount of margin in there to accommodate either in the setup, rather than taking a big yank of the chain later when you cut to it inevitably.
Okay, thank you.
Yeah, thank you. Right, sir.
So I wanted to go right back to the beginning of your talk with how you come to love the cloud and what is the cloud, and make a slightly different question on when cloud is worth doing. My point is that if you're running all your compute resources 24/7, 365, then certainly your cost, becomes less of a factor, and maybe a REMI model might be a much better option. So I just wanted to hear the panelists' thoughts on when cloud is a good solution, and perhaps when, say, having your system, on-prem and do a REMI might be a better.
So one of the things you need to consider is that the definition of cloud may be the same for public cloud versus private cloud in a lot of cases. In other words, so whether, who owns what is, and what are the fees for renting something that you don't own when you need it, things like that. That's something that we're not really having to delve into in this group, because we're just talking about how we move things from one functional cloud element to another functional cloud element. And I just want to share a little insight I had from last week. So last week I was out at the HPA, and the Hollywood Post Alliance is what they used to be called. I guess it's now the Hollywood Professional Association. They are going all in on cloud, okay? And it doesn't mean that every one of them is going to become AWS's best customer, although they are using those functions. What they're saying is that every single piece of media that they touch is going to go into a common storage base, and that anybody that needs to use that media is going to be able to extract it. So no more shuttling files from one post-production house to another. They're deserializing their production link, everything like that. So every single element, the script, the call sheets for actors to show up on set, every graphic that's designed, every element of a physical object that you're putting inside that you're modeling, et cetera, every single element ends up in their lake of data. And they're not there yet, but that's the way the industry is going. And I think we're going to be very much headed in that same direction.
Yeah, I think I'll get you in a second. One thing to remember, with STI, if you remember STI, routers came in certain shapes and sizes. And so it became this constraint that if you said, what should the workflow be? It turned into, well, the router's only this big, so the workflow has to be X. When we transitioned into IP-based workflows, yes, practical switches also come in certain sizes, but those sizes are gigantic. So suddenly, this technology constraint on the workflow stopped being constraint, and people had to actually think about, what are we trying to do, as opposed to what constraints do we have to navigate. Now, this lets people make a workflow decision separate from kind of a cost and technology decision, and that's ideal as a customer. Now, the same thing applies with dynamic scalable computing resources when you say, well, maybe I have some computing resources that I own that live in a room down the hall, and maybe I have some that I rent that live in the cloud. Ideally, if we do our job right as a standards community, we'll create a set of tools and techniques that separates that practical cost-based decision about what do I run where from the technology choices of how it's organized. That's my hope for the future. Carl, you have a question?
Yeah, it's more of a follow-up to what Wes said. In specifics, they're using, HPA did almost an entire day on the Movie Labs 2030 vision, which you can go Google that and see what it is, and showed several different examples and had different speakers talk about how and where the cloud is most appropriate, at least in today, and where they're going with this. And they picked the 2030 time frame, probably 5 years ago when they first started putting this together. It's really good information. The interesting part was that last year at the same conference, Renard Jenkins, who's now the president of SEMTI, at that time he wasn't, basically came up in a session on cloud saying that if you think you're going to be saving money on the cloud, you're probably not. But to think of it that the fundamental value of the cloud is efficiency and improving efficiency. And if you know how to do the business analysis part of that, you find you really will, in the long term, save money in the cloud, which I think is the big goal that everyone's after. It's the long term. The short term is don't expect the necessary return on investment that you probably will have to pitch to the CFO of the company in order to get it started properly. That's all.
Well, the good news is that 2110 and some of the other things that we've been working on are an excellent stepping stone to get to a fully cloud environment. And I think that, as an industry, we're going to see, it's just inevitable that so many more things are going to be done better, cheaper, faster in the long run in the cloud. And like you said, the flexibility is unparalleled. But I think the only people that are really going to suffer are going to be the couriers that used to bring hard drives from one production facility to another. I think the rest of us will do fine.
They're all working for Uber Eats now.
There you go. They got to deliver food.
All right, we got to.
By the way, the example also was very focused on cinematic motion picture production, which has far better uses right now for availabilities in the cloud. Television and live sports and those sorts of production activities are creeping along and getting closer and closer to reality. But the thought process and the development of figuring out how to use the cloud in an efficient and productive mode right now is extremely complicated.
Yep, absolutely. We didn't say it was going to be easy.
Mr. Gilmer, we yield.
All right. Well, thank you very much. Great panel, guys. Appreciate it.